Welcome, ladies and gentlemen, to our beginning of Chapter 5. This is going to be what's called analytic trigonometry. We're going to be looking at some very, very important identities. The first 4 sections of this chapter are basically solving some things and also proving some things. So I know some of you don't really like that word, but it's kind of a way of life in math. Same thing with like graphing. It's just a way of life in math. There's just no way getting around either proving things or graphing things. All right, and then the last 2 sections, 5.5 and 5.6, the law of sines, the law of cosines, are 2 super cool things that we can get outside of right triangles, because everything we've been doing is in right triangles, but trigonometry is not only about doing things in right triangle trig. We'll get outside. We'll see what that means as I get closer to that. All right, so today what you'll see here is we're going to be looking at our fundamental identities. You will receive a very, very useful bright yellow piece of paper in class that has all of our identities on it. It's kind of like a definition page that you're never going to want to lose. I have people in calculus that still use this thing because we need some of those identities in calculus. They're also very handy if you've memorized a few of them. We'll see what a few of them look like here for today. These are our fundamental identities. And the first couple ones are going to be basic ones we actually kind of know already. And the first is the reciprocal identities. For example, the fact that we know that sine is 1 over cosecant or cosecant's 1 over sine. And that goes along with cosine being compared to secant and tangent being compared to cotangent. These ones we've used quite often already because that's how we determined if I wanted to know, hey, what was the cosecant of pi halves or pi fifths or whatever. I guess if we pi fifths, then you would have to plug that in your calculator by doing this right here, 1 divided by sine. So this one's pretty familiar to us. The quotient identities might be familiar to you already. And I'm going to kind of show the proof of this before I even show you what the identity is, because we know that tangent theta on our unit circle is y over x. Well, we also know from our unit circle that sine of theta is equal to y, and cosine of theta is equal to x. Well, if that's true, we can just substitute, which tells me that tangent is actually a ratio of sine to cosine. So we can say that tangent is sine over cosine. Remember, these are all handy, and once you get the hang of them, you'll know why we need these identities. All right, so tangent is sine over cosine, which means that cotangent is the reciprocal of that, so cosine over sine. Now, here's those first few, those are pretty straightforward ones that you won't even have hard time memorizing, I don't think. You might have already memorized most of those. The Pythagorean identity, you'll want to think of Pythagorean theorem, where Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared. We know this to be true. People have proved this 1,000 different ways. It's always true, okay? So if you were to think about the unit circle triangles, again, so if we were to look at unit circle, and we looked at a triangle here, we had x, y, and 1. This would be a unit circle, right? Because all the radii are 1. Okay? If I did the Pythagorean theorem on this, I would have x squared plus y squared equals 1 squared. Well, that's what actually we're going to start with here. Every single triangle on that circle can be written this way. X squared plus y squared equals 1. But if we go back to that same idea I was talking about a second ago, where I said y is actually, not cosine. Sine of theta is y and cosine of theta is x. We again can substitute this in for x and y over here, and we get a very new statement to us. So there's two ways to write this. Normally we write the bottom one. So notice we took sine and we squared it, and we had cosine and we squared it. But we normally write the bottom one as cosine squared of theta plus sine squared of theta equals 1. But what I do want you to notice, because this comes up later on in this chapter, these two things are identical. And you'll even get to the things like cosine cubed of x, which is going to be the same thing as cosine of x cubed. Okay, so it's good and important to know that these two statements are the same with the parentheses or without the parentheses. And notice where we put the exponent for cosine and for sine here for these squared versions. Now, there are three variations, as you'll see on the yellow sheet. There are three variations. This is the basic one, and this is the one you should memorize. And the other two are based off of this. If I was to divide both sides by cosine squared, so I'd say, okay, cosine squared theta plus sine squared theta equals 1. And if I divided by cosine squared, and cosine squared, notice here I would get a 1. And then I know that sine over cosine is tangent, which means sine squared over cosine squared is tangent squared. Again, the use of parentheses there. And I know that 1 over cosine is secant, and therefore 1 over cosine squared is secant squared. So we get this first of our other versions. Okay, so if we divide both sides by cosine squared, I get this version. And you might guess that if I divide both sides by sine squared, I get the other version. And you'll see all three. This is our first, our most basic, and this is kind of 2 and 3. There's 3 variations of the Pythagorean identity. Try to memorize this one. This just comes from a squared plus b squared equals c squared. And then you can divide by either sine or cosine squared to get the other two versions. It actually is very helpful to memorize as many of these as you can, really. All right, so the next one. Oh, sorry, we're going to use the identities first. We're going to find sine and cosine if tangent is 5 and cosine is bigger than 0. So how might we do that? You kind of think about it for a little bit. And what we're going to do here is we're going to use the Pythagorean relation for tangent. Some of you might be trying to go, oh, sine over cosine is tangent, so sine over cosine is 5, but that doesn't actually tell me enough information to solve for both sine and cosine. So that one doesn't work. But I know that 1 plus tangent squared theta is equal to secant squared theta. And this will get it so I know what secant is, so I can find what cosine is. All right, so I get 1 plus tangent squared, so tangent is 5, so tangent squared is 25, plus, or sorry, not plus, what am I doing there, equals secant squared theta, which means secant of theta is radical 26. Well, if secant of theta is radical 26, I know that cosine of theta is the reciprocal of that. Now I can use my identity for tangent for sine and cosine here, and I can say, all right, well, I know cosine, so tangent equals sine over cosine. So 5 is equal to sine over what I know cosine to be. And then I can multiply both sides by this denominator here, and I can say, okay, sine of theta is equal to 5 over radical 26. And obviously you should simplify these. This is actually 5 root 26 over 26, and this is root 26 over 26. Okay, so there we get sine and cosine just by using these identities. Notice I didn't use any triangles here. It wasn't necessary to use any triangles at all. Could we have? Yeah, probably. But I really want us to become familiar with the identities. It's very, very important to us. All right, let's try another one. I want to find tangent and cotangent if secant is 4 and sine is less than 0. Notice, oh, I forgot to say anything about cosine greater than 0. Remember back here where 26 was equal to secant squared theta? When we took the square root of both sides, technically we would have gotten the plus or minus the square root of 26 equals secant theta. But it said cosine is greater than 0, so secant was greater than 0, so I had to use the positive version. Sorry, I forgot to mention that. Okay, helpful to us, obviously. All right, so let's kind of do the same thing here. Secant of theta is equal to 4. So we're actually going to use the same version here. So I'm going to say 1 plus tangent squared theta is equal to secant squared theta. And I know secant to be 4, so secant squared is 16. So tangent squared is 15. And if tangent is 15, sorry, tangent theta is square root of 15. If sine is less than 0, that just means cosine is less than 0 as well. But it can't be. So we got to figure out what we're doing here. What does that even mean? Oh, because back here, if I want sine to be less than 0, which is a negative number, and if I have secant, which is actually cosine, is positive, that means tangent and cotangent have to be negative because they're the ratio of sine and cosine. So that means this is actually negative radical 15. Which then, in turn, just says, okay, well, cotangent of theta is just the reciprocal of this. And I would get 1 over radical 15, which I would then simplify to this. All right, so not too bad. It's just manipulating equations, basically. All right, so let's look at a few other ones here. The cofunction identity. And actually, we've kind of looked at it a little bit already. And it was way back when we were first looking at sine and cosine. And for finding sine of 30, we know that's to be a half. This is degrees, by the way. I didn't put a degree symbol, not radians. Okay, so sine of 30 degrees and cosine of 60 degrees, you might remember or might be able to figure out that they're both 1/2. And I hope you know that 30 and 60 are very important numbers to each other because they are complementary. Complementary. Okay, they're complementary angles. They sum to 90. And that's what these cofunction identities represent. So the example that I'm going to give here is sine of 90 minus theta is equal to the cosine of theta. So in this example up here, the sine of 90 minus 60, which is 30, by the way, if you couldn't do that math, is equal to the cosine of 60. Or the sine of 90 minus 13 is equal to the cosine of 13. It doesn't matter what that theta is, it always comes out this way. The sine and cosine of complementary angles are equal. And there are other versions of this. There's actually 6 variations, and it's for each of our functions. There's one for sine, one for cosine, one for tangent, cotangent, secant, cosecant. The next identity, oh, I didn't say, there's a lot of identities today. The next identity is even and odd functions. And we've dealt with this before in our study of polynomials and functions in general. You might remember some of the variations of even and odd. This obviously is for symmetry of functions. If you are symmetric about the y-axis, you are considered even. That means you can fold the function on the y-axis, and you'll get the same thing on both sides. And that's what this statement is. If you plug in here, if you take your function and you plug in a negative value, you would get the same thing out as if you plugged in a positive value. And in our basic sense, cosine is an even function, which actually means secant is also an even function. And what you'll notice is secant and cosine are the only even functions, trig functions, because functions that are symmetric about the origin are considered odd, and that's if you plug in a negative value, it's the same thing as if you plugged in the positive value, you would just get the negative y value. And all the other four, sine, cosecant, tangent, and cotangent are all odd functions. And there is a usefulness in even and odd, and it actually comes from graphing. I gave a problem once where I gave this particular function to graph, and I had lots of people get it wrong because they forgot what this meant inside here. This negative represents a reflection across the y-axis, and this pi thirds represented a really weird phase shift that people didn't realize. And the way I'm going to do this is I'm going to think about even and odd, and I'm going to first factor out a -1, and I'm just looking at this thing on the inside of the tangent. So now I have the tangent of negative x minus pi thirds. But I know the tangent of a negative thing is the same thing as the negative tangent of the thing, right? Because we have our identity saying the tangent of negative theta is equal to negative tangent of theta. And that just means x minus pi thirds is my theta. Well, what this shows us, this negative x here, should have been a reflection across the y-axis. However, using even and odd, it actually shows that it's the same thing as a reflection across the x-axis. That's what I say here. So it shows for an odd function, if you reflect it across the y, it's the same as a reflection across the x. Okay, kind of nice, interesting thing to know. So where can we use those last two identities outside of the graphing? Let's say I gave you cosine of theta is equal to 0.34, and I want you to find sine of theta minus pi halves. Well, if you ever see something right here where it's something as a difference to pi halves, you should automatically think cofunction identity. And my cofunction identity says the sine of pi halves minus theta is equal to cosine of theta. Well, the thing is it's not pi halves minus theta, it's theta minus pi halves, which means I need to change this. And I know I skipped a step here, so I'm going to show this step. I'm going to say, well, sine of theta minus pi halves is actually sine of negative pi halves minus theta, just like I showed in that last example. And the sine of a negative angle is the same thing as the negative sine of that angle. And now I have the cofunction identity. Sine of theta minus pi halves, I have a cofunction identity, which means it's actually the negative cosine theta. Oh, that's actually it, right? Because it says that sine of Sine of theta minus pi halves is the same thing as the opposite of cosine. Well, I know cosine is 0.34, which means those two things are equal. Negative 0.34 is the same thing as this sine of theta minus pi halves. That's kind of cool. Again, no triangles, no calculator. You notice no calculator yet? I haven't done anything, even with 0.34. All right, here's where this stuff starts getting good. Okay, if you didn't think it was good yet, it's going to get better. And you know what I mean by better. All right, so here's a question. Notice there's no equal sign, so we're not solving anything. We're not proving anything either. This is basically saying, hey, simplify this statement. You know that you can do, okay, 3 times x and 3 times 3, I get 9. That's a simplification process. There was no equal sign in the beginning. It just said simplify. So what we're going to do is we're going to simplify this using our identities. So this is where it starts getting challenging. You need to be able to see the identities. You need to be able to see what identity to use. And since I see some cosine squared and maybe a sine squared in here, maybe Pythagorean, but I also notice that I have a sine here and a sine here, which means I can do a little bit of factoring. So if I do this, I say, okay, sine of x. And if I factor out that sine of x, I get sine squared x plus cosine squared x. Well, I know this thing using my Pythagorean identity. Sine squared plus cosine squared is 1, which means I get sine x times 1, which, well, oh, that's it. That means this big, ugly statement, well, ugly to you, okay, is just equal to sine of x. And that's a simplification process using our identities. What about this one? This is secant plus 1 times secant minus 1 divided by sine squared. So let's see what this does. If I have something that I need to multiply, that just kind of makes me want to multiply it, all right? So if I do secant plus 1 times secant minus 1, I get secant squared x. Notice they're conjugates, so the inner and the outer cancel each other out. And I get secant squared minus 1 divided by sine squared x. Well, this kind of looks like a Pythagorean identity. Secant squared x minus 1. Well, it is because I know that 1 plus tangent squared is equal to secant squared. Well, if I just subtract the 1 from both sides, that means this thing is equal to tangent. Well, that's not quite done. That's not quite done at all. So let's see what this does. I know tangent is actually sine squared x over cosine squared x all over sine squared x. Well, dividing by sine squared x is actually like multiplying by 1 over sine squared x. Well, oh, that's nice. Those cancel. So I'm left with 1 over cosine squared x. Well, I'm not done yet because now that's actually much simpler as secant squared x. And now I'm done. That's all farther I can really go with this one. But notice how much simpler that is than the original statement. Remember, whole idea of simplifying. One more here. Cosine x over 1 minus sine x over cosine x. And you're probably thinking, I don't even know where to go here. Well, probably since I'm subtracting two fractions, I probably need to make common denominators. Well, since neither of the denominators have anything in common, I need to multiply by each other. So I need to here multiply by cosine over cosine. And here I need to multiply by 1 minus sine over 1 minus sine. You think this is the only way to do it? No. I actually just realized there's another way to do it, but let's just go with this one. So I get cosine squared x over, let's just leave it right now. Sometimes I don't multiply things through because I never know exactly if I'm going to cancel stuff later. And I got cosine times 1 minus sine x minus 1 minus, or sorry, not 1. I get sine x not times again. What am I doing here? Minus sine squared x all over cosine x times 1 minus sine x. Oh, this looks kind of ugly, though. I don't know. Let's see. So cosine squared minus negative cosine, or cosine squared minus negative sine squared. Well, that's just cosine squared plus sine squared. So I can actually get this. I can look at this as being cosine squared x plus sine squared x. Well, I know that to be 1. So I actually get 1 minus sine x. So here I get 1 minus sine x in the numerator. And my denominator is cosine x times 1 minus sine x. Well, I hope you see that the numerator has something in common with the denominator here. And they have this 1 minus sine x in common, which means I get 1 over cosine x, which is secant x. See, it's not too bad, I hope. All right, I believe this is the last piece for this particular lesson. Find all the values of x on 0 to 2 pi that will satisfy this statement. That's kind of hard. But it's not as hard as you think it is. Because this is an equality, I can deal with equality. I can multiply both sides by sine. So here I'm going to get cosine cubed x. Basically, guys, by the way, this is all between 0 and 2 pi. That's just one time around the circle. What values am I going to be able to plug into this that will make this a true statement? So if I'm here, I'm going to multiply by sine, get rid of this fraction. I get sine x times cotangent x. Well, this doesn't really look helpful to me until I realize that cotangent x is actually cosine over sine, which means that cancels. And now I get cosine cubed x equals cosine x. Oh, I know these type of things. These are like polynomials. This is like a cubic function. So I can say it's actually cosine cubed x minus cosine x is equal to 0. And again, you know how to do this because I'm going to factor out a cosine x. And I'm going to get cosine x squared minus 1 equals 0. Oh, I know also for polynomials that means that cosine of x is equal to 0. And cosine squared x minus 1 equals 0, which means, obviously, if you add 1 and take the square root, you get cosine x equals to plus or minus 1. Now, here's the thing. You don't want just what is cosine. You want to know what is x. Okay, if I look at my circle, cosine is 0 at, okay, this implies, by the way, an equal with an arrow implies that x is equal to, pi halves and 3 pi halves. That's where cosine is 0. And then I also want to know, where is cosine positive or negative 1? Well, this implies that x is equal to, well, I know cosine is 1 at 0 and negative 1 at pi. And I know it's back at 1 at 2 pi, but I don't want to write 2 pi because I'm not going to include 2 pi in my answer because it's not part of the question. All right, so you'll notice that the stuff that we're going to be doing for solving is actually kind of along the same lines as solving normal polynomial equations, quadratics, cubics, that sort of fun stuff. At least I think it's fun. All right, but again, using all of our identities. Eventually, you're going to use the entire yellow paper. It's a whole front sheet of a piece of paper. It's all the identities. I think I've even got an identity on the back. All right, oops, let's get rid of this. I got one more question for us. What about 2 sine squared plus sine equals 1? Well, to me, this kind of looks like 2x squared plus x equals 1. And I know quadratics work like this. 2x squared, oops, let's get rid of the x squared. 2 sine squared x plus sine x minus 1 equals 0. And then I can factor just like I would a quadratic. I hope you can do this. 2x squared plus x minus 1 is 2x and x plus 1 minus 1. Oh, that means this factors the same way. 2 sine x minus 1 and sine x plus 1 equals 0. I can do the same thing I did a minute ago where I said 2 sine x minus 1 equals 0. And I can say sine x plus 1 equals 0. If I solved for sine of x here, I get 1 over 2. And here I get negative 1. Well, I know sine of x, and remember the same thing from 0 to 2 pi. Sine of x is equal to half at x equals pi sixths, which is 30 degrees. And where else? Let's say 150 degrees, which is actually 5 pi over 6. And I know that sine of x is equal to negative 1 at 3 pi halves. See, there we go. We get 3 answers, which is kind of counterintuitive, I guess. You can't think because it's a quadratic, there's only 2 answers, because these are not quadratic type of functions. They're not linear functions. They are reciprocating functions. They are oscillating functions. We keep going back and forth to certain answers. I'll get to the finding all solutions a little bit later, to looking at some of our double angle and triple angle identities coming up later. So here's your assignment. Again, you'll get an assignment sheet to go along with this, obviously. So when you get your trig sheet, your bright yellow piece of paper, that's going to be your friend for the rest of the quarter. It'll be your friend a little bit next semester, and it'll be your friend in calculus. So don't lose it. All right, have a good time doing this stuff. I enjoy it. I'll see you guys later.